As of now, in our discussion on resistors and electric circuits, we only really examined connecting resistors into circuits that carry a constant or direct electric current. Now let's examine what takes place within our resistor when we connect that resistor into a circuit that contains a voltage source that creates an alternating or changing electric current, a current that changes with respect to time. So, let's begin by defining the symbol that describes the voltage source that creates an alternating electric current. Now, this is the symbol that describes our voltage source that creates an alternating electric current. And this diagram B, describes our circuit that contains a resistor that is connected to our voltage source that creates an alternating electric current. Now recall that an alternating current source produces an alternating EMF, so a voltage that changes over time, and that in turn creates an alternating electric current that can be described using the following mathematical relationship. So, the electric current I is equal to I naught multiplied by cosine of omega multiplied by t. Now, the t is simply the time given in seconds, and our I is simply our electric current at some time given by t. Now, I naught is also known as our peak electric current. It's the maximum value of our electric current that is reached within this electric circuit. Now, our omega is known as our angular frequency, also known as the angular velocity. Now, notice our omega is given by the following equation. So 2 pi multiplied by the frequency given in hertz. And our peak electric current I naught can be given by multiplying the root mean square electric current multiplied by the square root of 2. So if we know the root mean square electric current and we multiply it by the square root of 2, we get our peak electric current given by I naught. So, we see that once we actually connect our resistor to an alternating electric current source, the electric current inside our resistor essentially oscillates according to the following equation. So it increases and decreases. Now let's describe what happens to our voltage across our resistor over time. So, what happens when an AC source is connected to a resistor? Specifically, what happens to the voltage? Well, the voltage across a resistor inside an electric circuit is given by Ohm's law. So, the voltage is equal to the product of the electric current inside the resistor multiplied by the resistance. Now, we just defined the mathematical relationship between our I and time. So let's replace our I with the following equation. So the voltage is equal to the product of the resistance, I naught cosine of omega times t. Now let's bring this r to this side, and we see that I naught multiplied by r cosine of omega multiplied by t. Now, what exactly is the meaning behind I naught multiplied by R? Well, if we take the peak electric current I naught and multiply by the resistance, we get the maximum quantity of voltage that exists between our resistor, inside our resistor. And that means this can be replaced with V naught, where V naught is simply the peak voltage given by the following equation. So V naught is equal to the product of the root mean square voltage and the square root of 2. So we see that the voltage is equal to V naught multiplied by cosine of the angular frequency multiplied by time. So not only does our electric current inside our resistor connected to an AC source vary, oscillate back and forth over time, the voltage also oscillates. So what exactly can we conclude? So we conclude the following three equations. So equation 1 describes the change in our electric current over time. Equation 2 describes the change in our voltage with respect to time. And these two equations are given by the following graphs. So we see that at an initial time of t equals 0, our electric current inside our resistor is essentially at the highest possible point. It is at the peak voltage. Now, as time progresses, the electric current inside our circuit essentially oscillates back and forth via the following cosine function. At the same exact time, the same thing happens to our voltage, as described by the following green curve. So, note that when the electric current is 0, the voltage is also 0. So at these 2 points, we see that our electric current is 0 and the voltage across the resistor at those 2 points is also 0. Likewise, when the electric current is at a maximum value, we see the voltage is also at a maximum value across our resistor. So because these two graphs can be essentially superimposed, that means that the electric current curve and the voltage curve are in phase. Now, let's conclude our lecture by describing what happens to our energy as the charge travels through our resistor. Now, whenever charge or current travels through a resistor, energy is lost in the form of heat. And the rate of change of energy with respect to time is the power. So the power output, the power lost within our resistor is given by the following equation. So because the voltage is equal to I multiplied by R, we can replace our voltage and we get the following result. So the average power that is lost within our resistor as our alternating electric current travels back and forth is equal to the square of our root mean square electric current multiplied by our resistance. So this gives us the power lost inside the resistor as a result of heat.